So
Yes.
today we've got Benjamin Misell, and he is talking about
Yes.
Tales of C, the 6502, and the BBC.
So, hello, I am Benjamin Misell. For those who don't know me, those are all the appropriate social networks. Let's get up a social network.
Yes.
Good, moving onwards. So this is Tales of C, the 6502 and the BBC, with added Python, because Python is awesome. So, first thing to point out, I'm not from the 80s if that's not abundantly clear. But I'm going to try and talk about something as if I'm from the 80s. So, our tale must start with going back to the 80s. Start with the BBC, with 80s appropriate logo, and their computer literacy project with this rather boringly titled and worded or laid out. It wouldn't be a PDF, but printed, whatever. But they wanted to get children to code. Same thing we're trying to do now, so maybe we haven't progressed that far. But they have a problem. What computer to use? Because microcomputers were just becoming a thing, and because the BBC were being the nice kid, they didn't want to pick favourites. So what they did was launch a competition with a list of demands for what it must do. And eventually, Acorn won, with the Acorn BBC Micro. If any of you heard of the Acorn Electron, it's the same computer just stripped down for the home market. So this was a seriously impressive computer for the time, actually. I've got one, that's why I'm doing this talk. And the Raspberry Pi's naming system is actually modelled after this, because this had Model A, B, and B+. So after a lot of history, Acorn won, but it did include telling the BBC that they had a computer ready, and the BBC said, great, we'll be round on Friday. This was Monday. So they had a week to make the computer, because it wasn't actually ready. All they had was some tactical drawings of some idea. So, quick quiz, who knows when this was launched, and when the computer literacy project subsequently started?
Friday.
No, I'm looking for a year, but very clever. It was 1981, and the computer literacy project started on BBC One on 1982. I don't have the exact date because I didn't have the time to go and look for that. And it's pretty advanced for a week's work. It has floppy drive support, 5¼ inch, although I have managed to get mine to work with 3¼ inch. A hard drive even. EcoNet, which was their local area networking thing. It was a bit like Ethernet, but not. Analog to digital converter, general input-output, parallel ports, printer ports, speech synthesis, interrupts, timers, 16-bit, 80-column color display with bitmap support, and even support for a second processor. So this was the bee's knees of the 1980s. And it's based around the 6502 processor, and it conveniently, the BBC Basic on it has a built-in assembler. So it's similar to MS Basic with additions that the BBC wanted for easier graphical routines. And I decided to learn Basic, but got bored because I thought it was just too verbose, too hard, and really hard to type on the keyboard, which mine, normally they're really nice, but mine's all gunked up and I haven't managed to clean it, it's so gunked up, so it's really hard to type on. Anyway, I then learned assembly. So this is all the instructions you can use in 6502 assembly. May look like a lot, but there are only, 53 of these. And the x86-64, if you went to the fourth talk, you'll know it's hard to define, but how I count it, it's about 1020 something. So this is definitely a RISC machine. And fun fact, most 64-bit x86 assembly programs actually use it like a RISC machine because all the fancy commands there are just so hard to use that nobody ever bothers. But this may look completely complicated, but once you understand the general mappings from a higher level programming language to assembly, it's not that hard. So I am now going to go through how an if looks. This does not look like a normal if, for those you can't tell, but it is comparing that 43 is less than 44. So we load, into the A register, the literal value of 43 hex, actually, and then we compare it with the literal value of 44, which is literally just does a subtraction, but doesn't actually do the subtraction, it just sets the flags as if a subtraction happened. Then we can branch on minus, because 43 minus 44 is a minus number. So if it is a minus, we jump to do the main code logic of the if, and then we jump past the else to the end of the if, and then the rest of the program. And if it fails, this branch will do nothing. Then we jump past the passing bit of the if to the else, and then continue with the rest of the program. So, at this point, something wasn't quite right in my brain. I thought, wait for it, but you probably know if you've seen the title of this talk, I can write a compiler. No. Bad idea. Turns out compilers are stupidly complicated. So, onwards with how does a compiler work. This may be the boring bit, but admittedly you've decided to come to talk about compilers, so I assume you'll stay. Section will be full of diagrams, so any diagram nerds, hope you're happy. And how long do you reckon this has taken me so far, considering all I've got to is implementing a function, so you can call a function written in assembly, but not call a function written in C, because it doesn't actually know how to compile functions yet. So it's taken about 2 months. What?
6 months?
2. But that's, yeah, 2 months of a lot of my time. So this is what a compiler do. It does. It turns code into other code. Rather simple idea, again, very complicated. Let's investigate that arrow a bit. So code does some things, and then other code, such as Alexa, Parser, and AST. So, step 1, Alexa. So Alexa turns all, not Alexa, although if anyone is watching this on YouTube, I'm sure it's activated. So this is possibly the simplest program ever. It could just return 1, but I decided to do 1 plus 2 so I could show a bit of how the maths work and whatever. So it turns into a series of tokens that can then be understood by the parser. So those are actual tokens from the compiler, that's how they're written, and you may notice that most of these have redundant values, but I still use them for debugging purposes, and for example, an integer here that is not a redundant value because that's actually the value of the integer, etc. It's probably the simplest bit because all it has to do is read a thing and mostly see things separated by spaces, or sometimes they can either be separated by spaces or not, whatever. It's only 211 lines, but that's the simplest bit. The next step is a parser and AST, and for those of you wondering, it has nothing to do with hyperactive, neatly trimmed trees that do things for you. So, the parser converts the tokens into an abstract syntax tree. It is called so because it represents the general point of the program without actually containing any of the original program. And it's a tree, so it can be walked with the next bit. But where was I? So there's the root node here, which is just an empty node that we start on, always. And this can contain many functions or global variable definitions. This is sort of the trunk, and then these are all the branches, and eventually you reach the leaves. Any of you have used trees before, I don't need to explain this, but for those of you who haven't, I will. So each node is a Python class, which all they do is store variables, so really it's not the best use of classes, but the class, anyway, I can then get the name of the class to decide on which function will then pass that class into assembly. And there are 440 lines that go through this, and I haven't even implemented half of the C standard. This is probably the most complete part of it. The for loop section is at least 200 lines. For loops are really hard to pass. I had to look up someone else's example of how they did it in a C compiler written in C, and then try and turn that into Python code based on, just forget it. So we're actually getting somewhere near assembly. Like these int literals here, they can simply be load the value into the accumulator and the binary add. That's one instruction. Return statement, okay. Compound statement, yeah, really, sort of. Next, and assembly. So this would be the output assembly with a lot of it stripped, because you can see we're starting at line 1240. Because this is basic, we count line numbers in 10, so you can easily insert lines in between here, up to 10 lines. Admittedly, I probably don't need to do that because this is not going to get edited, it's just going to get output, but sometimes I do edit it to try and figure out what went wrong. Let's have a look. So this JSR reset resets all the values used, because we use 0 page in this, because it only has 3 registers, the 6502. So 0 page is helpful because we only need a single byte to define the location, not 2 bytes, even though it has a 16-bit address bus. It will the 6502 will implicitly know that the first 2 bytes are 0. First byte is 0. And it takes 1 less processor cycle to process, so it's marginally quicker. So this is how we do. So we load the low byte of 1 and store it in a 0 page location. Then we everything is a pointer in this, by the way. So then we load the low byte of the stored location and store it in the low location of the pointer to the value. And I should also mention I implemented this in 16-bit. I could have done 8-bit, but I wanted to stick to the C specification, which says that integers must be at least 16 bits. Then we load the high byte of 1 and store it in the high location. Then we load the I'm confused now. Oh no, load the high byte of the storage location and store it in the high storage location, and then load the high byte of 1 and store in 0 page, and so on. And then this subroutine simply just moves that so all the bits can be chained together easily. So this whole section of code here is the section of code to load an integer literal, and then same here without the move, and then this is the add, so it loads all the values in from the pointed 2 locations, then actually jumps to the subroutine to do a 16-bit add, then loads the value back and stores it in the pointer location, and then we load the pointer again and store it in another 0 page location, which is the return location, and then we just read it out in BASIC. So if you've noticed this is horribly optimized, well, it's not optimized at all. There's no intermediate language in this at the moment. That's the next feature to add. And then I might be able to optimize it slightly more than this is. And this would be demo time if I could SSH into a BBC Micro. Trust me, I tried. So technically you could. It has a serial port which can be used as the input-output. So you can send characters in it, it will come as if it came from the keyboard, and any characters printed out will go to the serial port. And there are you could also do it via Econet, but I didn't have the Econet interface installed. I didn't fancy soldering one up and then trying to reverse engineer the Econet interface to make it work with a Raspberry Pi, say, and then copy that, just no. And it's actually RS423, which is a 5-volt version of that's 432, not 2, never mind.
485 is the other standard one.
RS232.
It's RS232 and RS485.
No, it's 432.
Okay.
It's a 5-volt version that's meant to be backwards compatible, but sort of isn't. I had some problems with that. So I went off and bought the right connectors, made up a cable, then plugged into an XP computer, because that's the only computer that had a serial port. Then I screwed the motherboard onto the top of the BBC Micro, and then a Linux VM on my main server that SSHs into the Windows XP machine. Yes, you can do that. And then that should then, in theory, send it through the serial port to BBC Micro. Surprise, surprise, the Linux to Windows XP bit worked, but the RS432 and the 2 serial communication standards did not work, probably because I'm trying to use a computer from the early 2000s with a computer from the 80s. It might have been easier if I had an older computer. Never mind, so unfortunately, no demo. And one final thing, how do variables work? Yes, those pesky things called variables that you all enjoy using. But I hate variables, at least when compilers are involved now. So we do it with a symbol table. So a symbol table, each variable is the symbol installed in the table, and that table then points to the memory location of where that variable will be. All the tokens, if you remember them, have an ID, and then the value of that ID is what goes in the symbol table. So here's the diagram. So we store the variable name. This is stored in the Python compiler and never actually put into the assembly. Store its type, so we know its length, and these are also arrays, so we just multiply the length of the type by the length of the array, and then we start the memory location and go on filling, although in the actual compiler's case it goes backwards, but let's just gloss over that. So yeah, the int size is 2 bytes here because it's 16 bits on an 8-bit computer, so location is down 2. But of course it isn't that simple because compilers and scopes. So a scope is like a function scope. Luckily in C there are only ever 2 scopes, the global scope and the function scope. But then there can be a function scope within a function scope. So it's never that easy. So time for another diagram. This is how it works. So we have the global scope storing these variables, then the local scope of first function and the local scope of the second function. As you can notice, these local scopes override each other. This is a flaw I actually noticed after I made this, that if you call function 2 from within function 1, then function 2 will overwrite the scope of function 1. So yet again, I need an intermediate language, then try and figure out the local scope from that intermediate language. Compilers are a pain. The global scope is fine, and local scopes, as long as you don't start calling functions from within functions, are fine at the moment. And with that, we conclude, I do believe. So, thank you. I've been Benjamin Misell. Any questions? Oh, actually, I see there is one question. What resources, blogs, books, website would you recommend for people interested in getting into... Actually, I can show this on the screen. Would you recommend for people attempting to write simple compilers? I actually read about 14 Python blog posts on a Python blog that someone wrote a Fortran interpreter, so instead of outputting assembly, it just ran the code, and that introduced me to the concepts of Alexa, a parser, how to implement a parser, how to implement Alexa, an abstract chain stack tree, and all of that. So I can't remember it off the top of my head, but I've since found out that someone has written a C compiler in Python for x86-64, and that's on GitHub. I think it's called Shimmy C. So if you want to go look at the code for that, or of course just Google Python C compiler or Python Fortran interpreter for the blog posts I saw. Anyone else got some questions? Yes?
It's not a question, but to add to that recommendation of sources, if people are interested in this kind of thing, there's a programming language called Lua.
Yes, I've heard of it.
It's really cleanly implemented in portable C, and it's possible to understand the entire implementation. It includes Alexa, Parser, and a compiler to bytecode and a bytecode interpreter. So it's a really good example of a real system that people use. It's also possible to understand.
Yeah, that might have been a slightly better starting point than C.
No, you're fine with this. It's good.
Yes, at the back.
We came in a little bit late, so I might have missed this at the beginning. Using assembly on the BBC Micro, how does that dialect of assembly compare to other dialects of assembly?
I actually didn't talk about that, but it's pretty much any 652 assembly you'll see for like Commodore 64 or whatever will be the same, except for the BBC, instead of using an ampersand for a hex value, uses a $sign. I don't know why, that's all I've noticed so far. Oh, and that you can exit out of assembly and do some basic and then go back into assembly and then use that basic value calculated in assembly. And then that basic value is compiled into the assembly when you run the compiler. Thank you. I think that's it.